this morning, we're happy to start off with Davide Gaiotto from the IAS, and he'll talk to us about BPS states in 2D and 4D.
Okay, so this talk will be based on work done in collaboration with Greg Moore and Andy Neitske over the last couple of years, and on some upcoming work with Edward Witten. Now, the main subject of this talk, or at least the motivation behind this talk, is the fact that four-dimensional field theories with n equal to supersymmetry, which basically means A supercharges, have or are associated to certain interesting integral invariants called BPS degeneracies. Which basically count the number of particles with certain charges which propagate in the theory and which preserves a certain amount of supersymmetry. Now, these four-dimensional theories are the field theory analog or something that might be more familiar to part of the audience, which are Calabi-Yau compactifications of type 2A or type 2B string theory. They have a lot of properties in common, and sometimes you can study a field theory by taking certain limits of a Calabi-Yau compactification. And BPS degeneracies, or BPS particles on the field theory side, correspond on this side to D-branes. But a sharp difference is that on this side, this is a subject which is mathematically rather well understood. There is a whole theory that is developed or is still being developed about what does it mean to have a D-brane in a Calabi-Yau compactification. So you can start looking at sheaves, the right category of sheaves, whatnot. On the other hand, unfortunately, I cannot quite tell you what is a good and precise mathematical definition of this BPS degeneracies in field theory. I mean, a weak coupling is pretty clear that there should be a rigorous definition in terms of certain indices or homology of moduli spaces of monopoles in 4 dimensions, monopole solutions in 4 dimensions. But I don't think I quite understand how one compute them just from the definition or from their field theory definition for general values of the couplings or in general locations of the vacuum moduli space of the theory. On the other hand, so we started studying this side of the blackboard because we are curious about this side of the blackboard. In particular, it was a reaction to work from Kontsiewicz and Solomon, which derived a wall-crossing formula. Basically, these BPS degeneracies, these integral invariants, depend on certain continuous parameters, which are typically called stability conditions in math, or the choice of vacuum for your theory. They are locally continuous, but they jump across certain walls of marginal stability. And this wall-crossing formula by Kontsiewicz and Solomon just gives you a prediction of what is the value of the invariance on one side of the wall if you know the value of the invariance on the other side of the wall. So it tells you how to cross the walls in the space of stability conditions. Now, it was derived or proposed based on the mathematics of categories of D-branes. But on the other hand, it seems to apply perfectly well to the field theory side. But nothing in the tools that they used or the mathematical frameworks suggests a simple connection to field theory. So this was the sort of puzzle that started the whole analysis. Now, in general, by now, there is a good number of proofs of the wall-crossing formula in field theory. These proofs have a sort of common theme. You deform your theory, modify your theory in some way, in such a way that the effect of this modification depends on the BPS spectrum, but at the same time is continuous across a wall of marginal stability. This puts a constraint on how the spectrum jumps across the wall. And this constraint every time comes back to just give this relation. Now, in the process, we've learned we had quite some fun with learning about various ways of modifying a theory. So we've learned quite a bit about defects in four-dimensional gauge theories with n equal to supersymmetry. In particular, the idea of a surface defect, of a codimension 2 defect, proves to be very useful. And also, we got progressively closer to the point where we could not just compute how the BPS spectrum jumps across the wall, but directly compute the BPS spectrum. So in the last few weeks, I think we've more or less completed the program, and now we know how to compute the BPS spectrum with pretty generic four-dimensional theory, just by looking how it interacts with some defects. And so the purpose of this talk is to present some of the tools that we used. And actually, right. So what do I mean with the defect? So suppose you have a theory in some higher dimensional space, say 4 dimensions. Okay? And then you modify your theory locally at some lower dimensional locus, say codimension 2 locus. Now, because of the properties of field theories of locality, if you do a local modification to the theory here, you're not going to affect the behavior of far-away excitations. So the behavior of the bulk four-dimensional theory is unaffected far away from the defect. But you introduce new degrees of freedom, new structure at the defect, and this structure is definitely affected by whatever is going on in the bulk. So by studying defects in four-dimensional theory, you can construct interesting probes of the dynamics of this four-dimensional theory. Now, a useful way, if you want to construct integral invariants, or in particular integral invariants that can be associated to, okay, let me say this better. So the typical modification that you can study in a theory is just a point-like operator. You modify the theory at one point. And then you can compute things like correlation functions. This typically produces for you a number, not an integer, but a real number, or a complex number. And but if you want to do something to a theory that produces an integer, possibly an integer that can be seen as a dimension of a vector space, it's actually useful to consider one-dimensional deformations of the theory. So why is that? So suppose you have a purely one-dimensional problem. Okay, so it's like quantum mechanics. You have a Hilbert space, and you can study the properties. Now, a very familiar setup is supersymmetric quantum mechanics. So it's a situation where your theory has a time translation symmetry generated by a Hamiltonian and two supercharges which anti-commute the Hamiltonian. Okay. So this is a very familiar and very useful setup because if you look at the quantum mechanics with the structure with some discrete spectrum, you have some distinguished states of zero energy which are annihilated by both supercharges. And then above, you have states with non-zero energy with coming doublets of opposite fermion number, which are exchanged by the action of the supercharges. So the work of it, and it's traditional to study the sort of indices which receive contributions only from the ground states, or maybe study the ground states themselves in the form of a Q cohomology. And because ground states can appear or disappear from the spectrum only in pairs, the index or the Q cohomology are very robust. So whenever you have a complicated theory, you have one way to break the symmetries to Hamiltonian and two supercharges in such a way that you have some sort of bound state, some sort of finite, discrete quantum mechanical system. You have a hope to define some interesting integrals and some interesting vector spaces. So now, in quantum mechanics, a classical example for this is the application to Morse theory, where you have a quantum mechanics defined by a real superpotential, by a Morse function. The supercharges, or in some manifold, your supercharges look like e to the minus h, d to the h, say. And then you can study the cohomology of the manifold by looking at the space of ground states of this sort of supersymmetric quantum mechanics. Or you can compute the Euler character of the manifold. Now, if you look at the system where you have a one-dimensional defect embedded in a bigger theory, something interesting can happen, though, because it's possible, as you tune the parameters of the four-dimensional theory, to get to a situation where you have an excitation which lives far away from the defect, and nevertheless have energy very close to zero. Now, if this happens, this picture is definitely not valid, because you have a continuum of particles which move very slowly in scattering states, which have arbitrarily low energy. So you have a continuum spectrum that comes all the way to zero energy. And whatever theorems that protect your Q cohomology or index fail. But for generic values of the parameters, typically these faraway excitations have energy bigger than zero. And then you have some continuous at some point above the zero energy, but who cares? So there is a general feature of these systems where, as you vary the parameters of your theory, these numbers or these vector spaces can jump. But crucially, the way they jump is always controlled by whatever zero energy excitations were available far away. In a sense, the only way you lose or gain states is because at some point they can be represented as a bound state, a very loose bound state of some bulk excitations to your defect. And this bound state radius goes to infinity as you tune the parameters, and you lose the state. So constructing this sort of one-dimensional defects is a good way to study the BPS particles of your theory. You can identify them, study them by the way they act upon this sort of numbers, which I will call frame BPS degeneracies in general in this talk. So they are sort of BPS states which live at a localized defect in your theory. Now, for most of the talk, I will focus on a two-dimensional example of BPS states and frame BPS states, so I will study two-dimensional theories with four supercharges, 2,2 supersymmetry. In particular, I will study Landau-Ginzburg models. Then, towards the end of the talk, I will embed these two-dimensional systems inside a four-dimensional system. And so I will have sort of chains of relations. I have one-dimensional systems which are affected by two-dimensional BPS states. And then four-dimensional BPS states affect the behavior of these two-dimensional BPS states. So ultimately, I compute four-dimensional BPS degeneracies, but I will do it by studying one-dimensional problems embedded in two dimensions, embedded in four dimensions. So what is a Landau-Ginzburg theory? To define a Landau-Ginzburg theory, you need two pieces of data. You need a manifold, a Kähler manifold, say, the complex plane, for example, I will denote points in this manifold as some x. And you need a superpotential. Which is an holomorphic function from your manifold to C. Say, in this case, could be a polynomial. In general, this polynomial, this potential, have parameters will come in families. So I have some interesting parameter space. Oops. Which I denote as C. And although the Landau-Gisborne model is defined starting with this data, my purpose would be to show how much of the physics can be just derived by looking at the properties of the parameter space. Now, so given this data, you can build a Lagrangian for a two-dimensional sigma model with certain amount of supersymmetry and blah, blah, blah. But so what are the basic properties of this theory? One assumption I will make is that for generic values of the parameters, the critical points of the superpotential, which are denoted as xi's, are non-degenerate. So at some codimension 1 Loci in parameter space, some of the critical points might coincide, and you can might get degenerate critical points. So, for example, here, when z goes to 0, this potential becomes cubic. Now, this assumption is useful because I want to study a massive two-dimensional theory, a theory which does not have light degrees of freedom. And the vacua of a Landau-Gisborne model on the real line are just given by a choice of critical point of W. And then the mass of elementary excitations around this vacua are controlled by the second derivatives of W. So I want to have a theory which is massive, a generic points in the parameter space. Now, this doesn't mean that there are no supersymmetric particles. Now, because the supersymmetry algebra, now for supercharges, I was saying, the supersymmetry algebra involves both the Hamiltonian but also a certain central charge. So it's possible for a state that has non-zero energy to still be annihilated by some supercharges. Now, these BPS particles take the form of solitons, where you have some smooth field, semi-classical, you have some smooth field configuration, which interpolates between two different choices of vacuum. So these BPS solitons satisfy some differential equation, which is basically a gradient flow equation. So the BPS solitons are states of the theory, which are killed by some of the supercharges. Which combination of supercharges depends on the phase, alpha. And the condition, classically, the condition to annihilate some supercharges can be written as this differential equation. Sorry, I should have written this as capital X. So I denote the coordinate on the real line as x. I go from x equal to minus infinity to plus infinity. And I hope that my calligraphic X and capital X's, well, they will, of course, occasionally get confused. Sorry for the notation. So these differential equations, Gaussian flow equations, have an interesting property. They have a conserved quantity. Because if you multiply them by derivative of x with respect of by the capital X or the little x, you discover that the imaginary part of w to the minus alpha is constant. And the real part of w to the minus I alpha grows monotonically. So what this means is that so if you just start at some generic point in the manifold and you flow, the flow will just bring you to infinity in a finite amount of space. If you want to find solutions that are well defined on the whole real line, so that asymptote at very small x and a very large x, I mean, it's easy to see that they are to asymptote and the very large x and very small x to some critical points. Furthermore, so these trajectories in the w plane look like straight lines with a certain slope coming out of the critical points. And unless you're lucky and you hit another critical point, you're just going to go to infinity in a finite amount of space. So these solitons only exist if alpha is tuned so that the value of the superpotential at the two critical points is real and negative, say. So as you tune this parameter alpha, sometimes you find a BPS state, a BPS solitons, which interpolate between two vacua. And it's not difficult to study how the number of these solitons jump as you vary the parameters for the superpotential. And this was done in full generality by Ceccotti and Waffa, for example. But now I would like to show you how to derive this sort of work-crossing formula, Ceccotti-Waffa work-crossing formula, by looking at frame BPS degeneracies in this system. They did it by looking at, say, the TT star geometry of the two-dimensional theory, which is a sort of an intricate way. So first of all, I need to break down the symmetry of the Landau-Klingberg theory to translations and two supercharges, which means I need to put a defect in the Landau-Klingberg theory, which breaks translation symmetry and breaks after the supersymmetry. Now, sort of familiar set of such defects is given by boundary conditions. You know, the most brutal way I can think of to break translation symmetry is just to put an end to the line, study the theory in a half line with some boundary conditions. But it's a little bit too drastic for what I want to do. Instead, I want to still study the theory on the full line. But I will let the parameters of the superpotential vary smoothly as a function of the position. So my superpotential is a function of the parameter z, and I let z vary as a function of the real line. I will keep the parameters far to the left and far to the right fixed to some specific values. And then I'll follow some path in parameter space between these 2 points. Now, if you just take the Lagrangian of Landau-Ginzburg theory and you plug this in, you're going to get something that's not quite supersymmetric. And you need to correct it a little bit to make it supersymmetric. When you correct it, you actually need to pick which linear combinations of the four supercharges you will preserve. And this is controlled by a phase again. A useful way to think about this is that we are just doing a quantum mechanics in path space. So you can take the standard formulas of the one-dimensional supersymmetric quantum mechanics and apply them to a functional of maps from the real line to your Kähler manifold. Something like the integral in dx of, let me get it almost right at least. Sorry. Sorry, right. Something like this should. Sorry. Yeah, something like this should work. Okay. So this sort of Morse function on the space of paths. The imaginary part of the superpotential. It's a choice of a phase. So constant. So for every choice of phase, you get a different defect. And then you can ask what happens as you vary the path, the initial and final values of z, and theta. Now, continuous deformations of the path don't do much. So now you can study this one-dimensional problem. You can try to define an index, even a Q cohomology, if you want to categorize things. And this way, you're going to build some invariants, some integral invariants, which are going to depend on many things. They're going to depend surely on the path, and the initial, including the initial and final points. They're going to depend on the choice of vacuum for your theory, and on theta. So you get a matrix of integers whose size is the number of vacua of your number of critical points of your superpotential. You can ask, what do these integers mean? Now, first of all, it's not difficult to argue that they are an homotopy invariant for the path, meaning that if you deform your path a little bit, you deform the profile of your parameters a little bit in the middle, but you leave the endpoints fixed. These numbers are not going to change. So they only depend on the homotopy class of this path. Another fun thing you can do is that suppose you want to study a path which goes from some z left to the right. I mean, suppose you want to write this path as the composition of two paths, P1 and P2. So you start your life with some jump in parameter space. Okay, it was defining its defect. And probably if you want to think about it as a localized defect, you want to keep this jump pretty sharp. But these integers can be computed for whatever choice of your profile. You can do it very, very smooth. Or if you want to study the composition of two paths, you can just do first a jump, wait for a while, and then do another one. So physically, you realized a certain Janus, a certain defect, as two defects which are separated by an arbitrary amount of space. So I wanted to study a defect labeled by a path P, and I can continuously deform it without changing the invariance into a defect for the path P1 and the defect for the path P2. And then locality basically tells you, because this is a massive theory, that all that's going to happen is that you have your Hilbert space decomposes into pieces, or you have a certain choice of vacuum in the middle. And so the integral invariants associated to P are just the sum over the intermediate vacuum of the integral invariants associated to P1 and to P2. So this means that this matrix of integers is really a very nice map from the groupoid of paths into matrices of integers, because if you compose paths, the matrices get multiplied. Yeah, theta is the same, always the same, sorry. For now, it's always the same. Now, suppose that your path was trivial. Now, for this to be compatible, it must be obvious that if your path was trivial, the matrix is just the identity matrix. But so let me try to understand the meaning of this integer invariance a little bit better. So we're studying critical points of this functional. So we're studying the differential equation. Just write it here. The same equation I had before. But the difference from what we were doing before, when studying solitons, is that now the parameters of the superpotential vary as a function of position. So this is sort of a driven gradient flow. It doesn't have a conserved chart, a conserved quantity anymore, so these flows can exist for every value of theta. Now, if you're not careful, right, if you don't tune things well, your flow will go to infinity in a finite distance, of course. Particularly if your path was trivial, we know that the only way to, for generic theta, the only way you can have a solution is that you just sit at the critical point at all times. So in particular, if you have very so because of this property, you can imagine decomposing your path into little subpaths and study the problem for each of these little paths. Now, it's pretty clear that if I'm moving just a tiny little bit in the space of parameters very, very slowly, and I'm at some value of the parameter space for which there were no BPS solitons, I'm not going to find any other solutions for this besides something that hovers very close to a critical point very carefully. So for most of this path, this matrix of integers is just the identity matrix, as it should, because otherwise the formula would not make sense. We surely don't want these integers to jump in a completely wild way as you vary your initial and final values of z. On the other hand, there will be some places along the path where you do pass to a point in parameter space where a BPS state existed, where a solution of these equations for almost constant z exists, which is non-trivial and jumps from different critical points. So now let me give a magnified version of that picture. What I'm saying is that in order to compute the number of solutions to these equations from some initial point to some final point along the path, what you need to do is to check when does this path cross the locations where the BPS equations had a solution with constant z. So the locations where the difference of superpotential between two critical points, I called wij before, belongs to e to the minus I theta times the real numbers. Sorry. So these are sort of codimension real codimension 1 walls in parameter space. This picture is drawn in parameter space. So I have walls where some BPS state of the Landau-Gisborne model exists. And at these walls, something can happen to this index. I can get a non-trivial contribution. This non-trivial contribution must have the form. I mean, I must be able to just keep sitting whatever critical points I was, or jump from critical point I to critical point j along one of the possible flows. So, in a sense, the contribution from a path that crosses a wall takes the form of a matrix which has a single non-zero of diagonal element, which I'll denote like this. So this is the unit matrix element, and this is just some integral number which is counting the solution to these equations with constant z, which means it's counting the BPS particles of the two-dimensional theory. So you see very concretely how the BPS particles of the original of the two-dimensional theory affect the properties of this frame BPS invariance. And actually, in this case, the frame BPS invariance can be computed in terms of the two-dimensional BPS particles invariance. Now, because this, so in particular, given a path, the matrix N is just the product, the ordered product of a bunch of these factors. For all the walls that are crossed by the path. Mm-hmm. Well, for a Landau-Gisborne theory, typically yes. I haven't encountered a situation where this product would not be finite. But also because, I mean, if it's an infinite product of matrices with integral values, it's going to be rather tricky to get a sensible result. Anyway, so some important properties. Now we're going to write some important properties about these numbers from the properties of these numbers. A crucial property was homotopy invariance. Now these walls can definitely meet. It's perfectly possible for the values of potential at a critical point I, j, and k, say, to align. But the problem is that the matrices that you associate to each of these walls do not commute in general. For example, 1 plus E1 2, so I should write up here, 1 plus E1 2, 1 plus E2 3 is definitely not the same as 1 plus E2 3, 1 plus E1 2. On the other hand, if you put a 1 plus E1 3 in here, this would be an inequality. So it must be true that whenever the walls meet, two walls meet, new walls are created or destroyed in such a way that the product of S factors crossing one way or crossing the other way is the same, because this was not a special point as far as these integral invariants are concerned. This was not a singularity of parameter space. So I should be able to just have an homotopy that goes from this path to this path. So this derives for you the Ceccotti-Vaffamore crossing formula, which indeed states that if you associate one of these matrix factors to each of the BPS particles of your Landau-Gisborne theory, then the product of these factors, ordered in an appropriate way by the phase of the superpotentials, is constant across the wall of marginal stability. So for example, here, this describes a phenomenon where on one side of a wall you had two particles, one between vacuum I1 and 2, and one between vacuum 2 and 3. On the other side of the wall you have three particles. A new particle from vacuum 1 to vacuum 3 has been created. Now, unfortunately, I cannot keep talking about this two-dimensional system, but there is a lot of fun things that can be understood about these integral invariants in terms of Morse theory. For the ones in the audience who know what a Lefschetz symbol is, these integrals basically give you the basis transformation between the Lefschetz symbols at some value of the parameters and the Lefschetz symbols at some other values of the parameters. And it's interesting to think that these numbers actually are dimensions of vector spaces. And you can make contact to start some two theories of derived categories of symbols and things like that, which allow you to study these vector spaces. I should also say that this setup can be usefully generalized to situations where your parameters, where your moduli space X, your superpotentials were a little bit exotic. And for example, we got a certain amount of mileage in studying knots with Witten by looking at certain superpotentials. Looking at Chern-Simons function as a superpotential in the space of complex flat connections on a manifold, and then looking at these invariants. Because you can recover sort of things like the braid group representation for the Jones polynomials. I mean, pretty much whenever you have a Landau-Ginzburg theory with an interesting parameter space, this gives you interesting representations of the homotopy groupoid of the parameter space. OK, but let me try to use the last maybe 5 minutes optimistically about the connection from 2D to 4D. So you see, suppose you look at one of the walls in parameter space. Let me just erase a little bit here. Okay. So to each of these walls, you have attached a certain difference of superpotentials, which is negative. Okay. So this difference of potentials is a real number. Typically, will grow monotonically in one direction, decrease in the other direction. And you can sort of follow a wall in the direction where this is becoming smaller, and the absolute value of this is becoming smaller and smaller. Now, two things can happen. Either this wall at some point disappears in some wall crossing process, because in a sense it has been created by other two walls, or this number is just going to go all the way to 0. So if I take a wall, I follow it backwards. These numbers are additive when you create new particles. So either it goes to 0, or this was created by two other particles whose numbers are smaller, and I can follow them backwards all the way to another creation event, or ultimately to 0. Now, when the difference of potential between two critical points is 0, the two critical points actually have to coincide. Because remember, this was not just the difference of potentials, it was the difference of potentials along a flow joining the two critical points. And this was a number which was increasing monotonically along the flow. So the only way it can be 0 is if the two critical points were actually coinciding. So these walls always end on special loci where two critical points coincide. So some new massless, some new physics is happening. And just so near this loci, the superpotential can always be approximated with a cubic superpotential. You can study in detail what sort of flows exist there, what sort of short flows, if you want, exist there. So how many lines come out of one of these points. You find out that there are always 3 lines coming out of type ij, ji, or ji, with a very specific s. So it's always things like 1 plus eij, pretty much. So this means that you can reconstruct the whole network of S lines, because every S line either came out of a wall crossing event or came out of a turning point of one of these points, or two critical points coincide. So vice versa, I can just look at all these loci in codimension 1 loci in parameter space, emit a wall, 3 walls from each of them, propagate the walls out, and if 2 walls meet, use the wall crossing formula to see what comes out, and just keep going until you populate the whole parameter space with walls. So the whole network of S walls is essentially captured just by the behavior of the local system of vacua on the parameter space and by these numbers. So I lost all the information about the original superpotential, only kept these numbers. Okay. Now, you can just now forget about the original superpotential and just apply this construction to a more general set of numbers. And this is what leads to the four-dimensional setup. So essentially, when you have a two-dimensional theory, lambda theory, always have these numbers. But if it's embedded in a four-dimensional, has a defect in a four-dimensional theory, you still have these numbers, but they do not come from extremizing a superpotential, which is a function of x and z. So you end up with some multi-values functions and with more general properties. And something can happen that does not happen in two dimensions, which is as you can look at the behavior of this S network as you vary theta, the parameter theta. You can encounter a situation where you have wall of type 1, 2 going one way and a wall of type 2, 1 going the other way for some value of theta. And so for that value of theta, they go the opposite way. Now this will not happen in a two-dimensional theory because here W12 is positive and here is negative. It's not possible for this to happen simultaneously. But when this is a defect in a four-dimensional theory, it can happen. And then you get a new type of discontinuity in your integers. Because 1, 2, and 2, 1 walls do not commute. The result of doing this is different from the result of doing this. So there is a new way your integral invariance can jump by a certain new type of transformation. This transformation turned out to be the transformation that Concierge and Soberman used to define their wall crossing formula. And so you finally connect back to the four-dimensional BPS states. And you can actually compute them, because you can compute the S network, you can compute the way it jumps and changes, and so you can compute the case transformation, you can compute the BPS spectrum, et cetera, et cetera.
Questions?
What's the embedding of the important?
Well, so you just need to define a four-dimensional defect in four-dimensional theory. If you have at least one gauge group, for example, there's a canonical way to do it by Hooker and Wittgen, where you see you have an SU2 gauge group in four dimensions. You can break the gauge symmetry to a U1 along the defect, and then you can now return to the Lagrange, which use this breaking. This is a symmetry. You can take the integral of the magnetic field in this U1 along the defect, or it poses monotomy to the gauge fields that live in this U1. So this way this always gives you canonical surface operators, surface defects, which have an interesting parameter space. And so you can play this game. So in principle, using this method, you can compute the BPS degeneracies of any theory, for example, which has pretty much any theory which has at least one surface operator, one surface defect with an interesting parameter space.
Other questions?
Can you explain something? In Concierge and Soberman wall crossing machinery, it never happens that this concept that walls can meet.
Yes, it does.
Does it? Can you explain that?
I mean, you can study the Coulomb branch of you can take a four-dimensional theory, say, pure SU2, whatever. It has a Coulomb branch. Okay. And then in this Coulomb branch, you can just draw walls, draw lines where so for every BPS particle on the spectrum, which has a charge, gamma, has a central charge. You can draw the lines in the Coulomb line where the central charge has a certain case. Now, to each of these lines, you can attach the corresponding KS pattern. So it's a certain transformation, which depends on the BPS degeneracies with the charge. It's surely possible for these walls to meet, and it's surely true that when they meet, new walls have to be created using the KS formula. So the KS formula can be seen as a compatibility condition on this network of K-walls in the column line, the column branch. It guarantees that the product of K-walls is an homotopy line.
Other questions? Okay, let's thank Davide again.